uh, beamforming techniques used in millimeter wave. Okay, uh, and yeah, so I'd like to take up some questions now. Yeah, kindly let me know if there is any question. Just a minute. Yeah, okay. Uh, yeah, I hope there is no questions. Let me move on to. Uh, I hope I am audible and my screen is visible. Can someone please acknowledge? Yeah, yeah, yeah. So the next topic we are going to see is the full duplex communication. So right now, one may say that we are having full duplex communication. We are having full duplex communication, but it is not full duplex. Okay, so say LTE. Okay, LTE uses two different types of duplexing techniques. One is FDD, frequency division duplexing, and time division duplexing. What does that mean? Is within in frequency division duplexing, the uplink and the downlink are separated by two different frequencies, and in the time division duplexing, different time slots. So definitely they are not a full duplex communication. Okay, because if you are using in FDD-LTE, 10 megahertz is allotted for uplink and 10 megahertz is allotted for the downlink. So what happens at the transmitter? So only if same frequency and at the same time transmission and reception is happening, then only we can say that as a full duplex communication. So is that possible? Even if it is possible, why it is not executed so far? That is a question that has to be answered. And this full duplex communication is actually proposed by Stanford University recently by a scholar called Dinesh Baradia. He is from India only, and this this is based on something called self-interference cancellation. So, what is the self-interference cancellation? Firstly, we want to know what is the transmitted power and the received power. Transmitted power is zero point 0.1 watt, and the receiver power is 0.1 nanowatt. You could see there is a large dynamic range between these two powers. Okay, like say one is 20 dBm, another one is minus 70 dBm. So you could see around a minus 90 dBm of difference between the transmit power and the received power. So uh, so how they are going to view this, how they are going to utilize this property for full duplex communication. So in full duplex communication, uh, the transceiver, consider a transceiver. Okay, transceiver is a unit which has both the transmitter and the receiver. Okay, so whatever information that is being transmitted, that is actually known to the receiver too as a unit. You consider a mobile phone, it has both the transmitter as well as the receiver. So whatever information that is being sent, that is known to the transceiver. So if I am receiving if I am receiving the transmitted signal at the same frequency, then I can easily subtract whatever information we are sending. We can subtract, that will be received too, that will be received in your receiver too. If you are using the same frequency, that will be received in the receiver too, along with the actual receiver frequency, I mean actual received signal. So in the receiver chain, whatever will be entering is, it will have both the transmit information as well as the actually what information has to be received, that information will also be there. But the one advantage we do have is this transmitting frequency, right? This transmitter signal, right? This transceiver is aware of what signal is being transmitted. So overall, if you are subtracting the received, the received signal from the signal that is being transmitted, so we can recover whatever signal that is being received. Okay, so this can be explained through the circuit that has been already available. So this is the conventional transceiver design people are using now. Okay, let's say FDD, frequency division duplexing, F1, F2. Okay, there are two different frequencies. At two different frequencies, the transmission and the reception are happening. Okay, so of course we have a power amplifier at the transmitter and the low noise amplifier at the receiver, and we have a duplexer circuit here as well. Okay, so what happens is it will be switching between the transmitter and the receiver. Okay, so with the same antenna, we could able to transmit at one frequency and receive at another frequency. So this basically this duplexer operates at two different frequencies. Okay, so even though it is a 3-terminal device, it could able to operate at the two different frequencies. So it has some attenuation of 50 dB. Okay, now coming to this successive interference cancellation. Okay, in the place of duplexer, we are going to use a device called circulator. Circulator operates at the same frequency. Okay, circulator operates at the same frequency, and this circulator, what it does is, it will operate at one frequency, and we are going to operate our transmission and reception at the same frequency. That means just don't consider about the transmitter chain. Anyway, transmission will be happening. We don't have to worry much about that. But in the receiving, you just imagine, while in the receiver chain, I will be getting whatever that is transmitted, I will be getting here, and whatever that is actually received, actual signal that has been received, that also I will get, because the transmission and reception are happening at the same frequency. So when both the signals are going inside, somewhere I want to cancel this transmitted information, as this fellow is near. Just a minute. Okay, so we have a LNA and a low noise amplifier at the receiver, and but the signal that is being received, the transmit signal and the actual received signal will be coming together. So we want to cancel this the transmit receive signal, the transmit signal that has been passing through there. Okay, so that is why we call this as a self interference cancellation. It's not successive interference cancellation, that comes for NOMA. This is self interference cancellation. Why it is called a self interference cancellation means, because we are in the receiver chain, we are going to cancel our own signal, our own transmit signal. Okay, so how this has been done, but this is not as easy as we say. Okay, because there are a lot of practical difficulties are there. Okay, we may think that two tones has been sent. Okay, we may think this is what we expect. We have sent two tones like that, but what is actually been sent is, that means what actually been received at that receiver means, you could see what these are all the harmonics. Harmonics will also be entering into the receiver chain, so we have to deal with that too. Okay, and make this, but actually the original two tones will be going at the higher power, at the higher power range, but some substitute fellows are also will be joining them. Okay, so this is the full duplex. This is one problem with the achieving this full duplex communication. That's why there was a question like why this cannot be done in way back in it would have been, this idea would have been proposed way back, right? But it is not proposed because of such complications. So how they are going to do that? So this is a circuit by Stanford University. You could see there is a cancellation that is happening in the analog side and as well as the digital side. And in the analog side, they cancel the signals are being cancelled such that the basically in analog side, why the cancellation is happening is because we have to make the received signal to be less than the actual received signal. That is, the transmit signal that is entering the receiver chain should be less than the actual received signal, because else what it does is it will drive this low noise amplifier to a non-linear region. Okay, to a non-linear region of operation, and there will be a lot of problems with that. So there is some kind of analog cancellation is required, and ultimately another type of cancellation, that is a digital cancellation, will also be happening, such that we will bring down this transmit signal that is entering the receiver chain below minus 90 dBm. Okay, so this is the idea behind this self-interference cancellation, and you could see this is due to analog cancellation, and this is due to the digital cancellation. Okay, and you could see the signal is being transmitted at a 20 dBm. The signal that is being transmitted at 20 dBm is entering in the receiver chain. Okay, fine. So this is another model proposed by the Rice University. Okay, and they mimic the transmitter chain. Okay, they mimic the transmitter chain, and they try to cancel the receiver signal. And there is one more thing that is proposed by IITM. I don't remember the exact design of that. Okay, so these are all the this is the self interference cancellation, and we have simultaneous wireless information and power transfer. Just 1 minute.